Linear approximation and differentials. In this section, I will talk about the linear approximation, which is a tangent line application. That means we will look one more time for tangent line application. Let's look at this graph. This graph represents a function f of x and its tangent. And the tangent line is attached, is tangent at the point A, f of A. And we will look really closely at this point of tangency. If we will zoom in and go extremely close, let's look at this, we can notice that, I can actually come back, we can notice that the line and the function itself becomes almost the same thing. The curve becomes more flat and we can't distinguish the difference between a function and the tangent line. That means zooming towards the point of the graph of at that point, the graph looks more and more like a tangent. That means this is one of the things that we can use a tangent line instead of the actual curve to, for example, approximate a certain values. Because the idea is that it might be easier to calculate the value which is on the tangent line rather than on the actual curve. Because the actual curve may be, it could be like a, not really a linear function, could be power function, high, like high degree polynomial, or could be exponential, could be logarithmic, trigonometric, and if we have to compute a values close to that point, we may get like quite complicated numbers. But a tangent line is always a line. It's always a linear function, which the equation is mx plus b. That means evaluating a value, finding a y value, we can substitute instead of x any value, even like a decimal, even a tiny number, and multiplying by m and adding b is not a complicated process. That means that's how we can use a tangent line, and we will call this as a linear approximation or tangent line approximation. That means let's get an equation. Okay? That means we will focus on tangent line approximation to the curve near to the point A. Let's look at this. We remember the equation of the slope, the formula for the slope, y minus y1, x minus x1. Now, slope in terms of calculus, of course, we know that is derivative at the given point. And one of my point was a f of a, and one, let's say xy. I will take this equation and multiply both sides by x minus a, and now solve completely for y. Which actually this line looks like a point slope form, point slope. And this is the same thing, but just different order. That means this equation will represent a tangent line, and we will call an approximation by the tangent line, linear approximation. That means let's take this equation. Okay, and this is my equation, and I can approximate original function by the tangent line. And this approximation is called the linear approximation, as mentioned before, or tangent line approximation, or just the linearization. Everything of the function f at a. Okay, and this is the equation. And since we call linearization or tangent line, we will use L of x notation. But I would like to make a small comment. If for some reason you will forget this equation, which states f of a plus f prime at a, times x minus a. Please remember, this is nothing different like a tangent line at a. Previously, we were looking for the equation of the tangent line if the given point was provided. I mean, if the point was provided. That means please note that this is simply equation of the tangent line. But using this as an approximation, using this equation, we will call linear approximation. And let's do the first one. Find the linearization of the function square root of x at 4. Makes sense because 4, I can easily compute square root of 4, the actual value, but possibly I can use this linearization to approximate the value which is nearby, like 4.01, for example. What is the square root of 4.01? Of course, not using a calculator. Linearization. That's the new formula. Linearization, which is the tangent line, it's representing by this equation, f of a plus f prime at a times x minus a. A is 4. Now the value at 4 is square root of 4, which will be 2. Derivative of the square root of x is 1 over 2 square root of x, but instead of x, I'm putting 4 and 4. Okay. 2, 1/4, and I can distribute 1/4 multiplying by x and multiplying by -4, and I am getting 1/4 x plus 1. That means this is my tangent line to the function square root of x. Let's see how this looks like. Square root of x, and at 4, we will have tangent line. Okay, and I can use L of x, 1/4 x plus 1. And we can see close to the point 4, the blue line and the actual curve looks almost the same. So now what we can do, let's use this linearization from example 1 and approximate the value of the square root of 4.05. That means 4.05, I believe it is relatively close to 4. That means I am allowed to use linearization at 4. Function square root of x could be approximated by the linearization close to 4, and that was the linearization. That means function root x, it's almost the same, like 1/4 x plus 1, but only for all of the x's near 4. Okay, and I can come up now, we can see just the values like close to 4. Okay, and now I have to approximate square root of 4.05. I can substitute instead of x 4.05, and hopefully without the calculator to do this basic operation. 4.05 divided by 4, it will be 4 divided by 4 is 1, and 500 divided by 4, it's 125, of course, paying attention to the decimal points. And plus 1, 2, 2.0125. That means that's the square root of 4.05 using the approximation. And I did use a calculator. I have a real value. Okay, that's what we can see nicely that they are quite close. This one, the original value, the real value is 2.0124. Our value is 0.125. Okay? That means what we did, we overestimated a little bit, of course, slightly. But now the question is why? Why we overestimated? I can draw it actually again. I hope you have the answer right now. Square root of x, and instead of exact value, I am using a tangent line. Okay? that we can nicely see value 4.05, right? Tangent line, it's above the curve. That means instead of getting the actual value, which will be the red dot will be the actual value, 2.0124, I did use the tangent line value, okay, which is 2.0125. And since the tangent line is above the curve, of course, we overestimated. But we can see, of course, I put the value far away. It is really, really close because we can see the difference between these 2 points are not big. And the red value will be not possible for me to get it, but the blue one using the linear approximation was relatively easy. That means that's the point, that's the application of the tangent line equation. Okay. Oh, and I do have actually the graph. Yes, we can see the square root of x, and the blue line is the tangent line. And please note, always when the tangent line is above the curve, we will overestimate. If it's below, we will underestimate, but still good approximation. Okay, I have another one. Find the linearization L of x of the function sine of x at 0. Linearization f of a plus f prime at a, x minus a. A is 0. Sine at 0, derivative of sine of x is cosine of x, cosine of 0. Sine at 0 is 0, cosine at 0 is 1. That means, simplifying everything, the linearization, the tangent line is just x. This means that function sine of x behaves like x near to 0. Okay? And we can see we do have a sine function, and that line is a tangent line. And at 0, doesn't really matter if I will take sine or x. And of course, function x, the linear function, is much, much easier to compute things. Okay, I have another one. Find the linearization of L of x of the function x to the power of 3 over 4 at 16. Linearization, which is the tangent line, L of a plus f prime at a, x minus a. A is 16. 16 to the power of 3 over 4. And now derivative of the function x to the power of 3 over 4 will be 3 over 4. X to the power of 3 over 4 minus 1, it's 1/4, which I do have here. And instead of x, the a value, 16. Now, we have to evaluate 16 to the power of 3 over 4 and 16 to the power of negative 1/4. Okay, 16 to the power of 3 over 4 means the 4th root of 16 and cube. 4th root of 16 is 2, 2 cubed is 8. Okay, and 16 to the power of negative 1/4, it's 1 over 4th root of 16. 4th root of 16 is 2. That means it is 1/2. 1/2 times 3/4, 3 over 8. And I can distribute everything, and that's my linearization. That means function x to the power of 3 over 4 behaves like the tangent line, 3 over 8x plus 2, only near to the point 16. Okay, another example. Use a linear approximation to estimate 2.001 to the power of 5. Okay, that means now we can see we do have a value that we have to approximate, but the function at the actual point A is not really provided. Based on the number that we're looking for, we have to identify a function at the value A. That means what we see a quantity x to the power of 5. which means the function will be x to the power of 5. And at some point, I will substitute 2.01. And the closest, nicer value, it's 2. That means my point A is 2. If I will find a linearization to the function x to the power of 5 at 2, I can use it for point 2.01. And that's the question. Okay, linearization L of x equals to f of a plus f prime at a, x minus a. A is 2, of course. Remember, A is 2 because we always operate with the nice integers, I can say. 2 to the power of 5, derivative of the function x to the power of 5, of course, is 5x to the power of 4. X is 2, A is 2. 32, 80, and I can distribute. That's the linearization. That means function x to the power of 5 could be approximated by just the line 80x minus 128. And now I have to estimate 2.001 to the power of 5. Instead of x, in the linearization, I'm substituting that number, 2.001. Multiplying by 80, subtracting 128, we're getting 32.08. And taking the actual number to the power of 5, like by hand, I will probably have problem to get this number. I mean, long process. That's the thing that we can approximate. Okay, example number 6. Suppose that f of 3 equals to 4, f prime at 3 equals to 6. Use the linear approximation to estimate f of 3.02. That means some information are given of the function at 3 and f prime at 3. Derivative at 3 is also given. And we have to approximate a function at 3.02. We don't really need exact the formula of the function because we do have important values. Linearization at 3, f of 3 plus f prime at 3, x minus 3. F of 3 is 4, f prime at 3 is 6. And I have my equation. And that's another nice thing. Without having an actual formula, having only a certain value, I did get a tangent line, equation of the tangent line. That's amazing. And now, approximating a value of the function, because function could be approximated by linearization, by the tangent line. That's me taking a tangent line and instead of x, substituting the value that we're looking for, 3.02. Multiplying by 6, subtracting 12, we're getting 4.12. 4.12. And this is the same one. You might try to pause the video without the solution and try to get the solution, 2.6. I have another one. Use the linear approximation to estimate tangent of 44 degrees. Okay. That's we can definitely see that my function will be, oh, I didn't write. Function is tangent of x. And the a value is 45, but we can't really use degrees. I have to use numbers, radians, pi over 4. And then if I will get a tangent line to the tangent function at 45, I can approximate tangent at 44 degrees, which of course I have to change 44 degrees for radians. Okay, let's get the approximation, linearization. Linearization is equal to f of a plus f prime at a, x minus a. A is 45. Oh, I did type the function. 45, which is pi over 4. Tangent at pi over 4, get ready with your answer. Derivative of tangent is secant square of x instead of x, pi over 4. Tangent at pi over 4, of course, 1. Secant at pi over 4, it's 1 over square root of 2. Squaring, it's 1/2. And we can distribute, and we do have linearization. Okay. Now, instead of x, I can put 45 degrees and get the approximation, because I can approximate, actually I do have here, I can approximate function tangent using a linearization. The only thing is, what I also did, I did copy this form, and I can show you why. Of course, the red box is nice, because it's nice mx plus b, slope-intercept form. This one is still not simplified. But one thing that we can see right away from the blue box, from the blue form, we can see the difference between the actual point A, pi/4, and how far away we're going from that 45 degrees. And because this is that difference, x minus pi/4. And since, of course, it will be right, but this is just for the learning purpose, 45. X, the value that I'm looking for is 44. That means I am going away 1 degree. And as we can see, this is 1 degree. Rather than substituting instead of x the value here, that's the same thing. But then we can see right away. But what I have to do, first of all, 44 degrees is 44 times pi/180. You remember how to convert from the degrees to radians. -1 will be just pi/180, negative pi/180. That means that's what I'm doing. 44 pi/180 minus 45 pi/180, which this is pi/4. And the difference is -1. -1 in radians is simply negative pi/180. Negative. And multiplying by half, I'm getting negative pi/360. And getting common denominator, I have this weird number. Of course, looks weird, but that's equal sign between. If I will put instead of pi, let's say 3.14 or just 3, I can get a number. Okay, that means this is tangent. This is tangent of 44, tangent at 44 degrees. But please note on the blue box the difference, because we have to operate like how far away I'm moving, either way, right or left, from my actual A value. Okay. And I have this question, similar that we just did. Use the linearization to estimate square root of 7. That means this one is telling me right away that my function is square root of x. Okay. I will write, I'm looking for my main formula, square root of x. And now, what is the A value? The A value must be the closest number to 7 that I can get the square root of. I mean, I think square root of 9, is the number, is the integer. Okay, that means 9 will be my A value. F of 9 plus f prime at 9, x minus 9. Function is square root of x, square root of 9. Derivative of square root of x is 1/2 square root of x. 1/2 root x instead of x9. And we can substitute. And also, I did simplify, but what is important, it's maybe to remember that we can use that form for the approximation. That means square root of x would be approximated by this, because x minus 9 is telling me how far I'm going from number 9. That means if I want the approximation at 7, I'm moving 2 units left, which will be -2. And let's, okay, I didn't compute. Let's approximate square root of 7. Actually, I can write here, square root of 7. It's approximated by 3 plus 167 minus 9. 3 plus 1/6, and the difference is negative 2. Okay. 3 minus 1/3, 2 and 2/3, and I can leave it like that. Okay. That means the value of square root of 7 is 2 and 2/3. We can see it's nice to use this difference. If you will substitute to this one, you will also get the same number. Okay, thank you.